This video is brought to you by mywayteaching.com.
So, as I told you in the previous part, that is the part taken by a fluid particle under a steady flow, we call it as a streamline. So, that streamline is defined as a curve whose tangent at any point is in the direction of the fluid velocity at that point. Okay, consider the path of a particle as shown in this figure A. So this is the path of the particle. Okay. The curve describes how a fluid particle moves with time. And this curve PQ is like a permanent map of fluid flow, indicating how the fluid streams. No streamlines can cross. This is already known to us, isn't it? So if they do, an oncoming fluid particle can go either one way or the other, and the flow would not be steady. Hence, in a steady flow, the map of flow is stationary in time. So if we intend to show streamline of every flowing particle, we would end up with a continuous lines, number of lines. Okay, consider the planes which are perpendicular to the direction of fluid flow at 3 points, that is at point P, R and Q, as you can see in the figure. So here we are consider one plane which is perpendicular to the fluid flow, and the plane R and the plane Q. So the plane pieces are so chosen that their boundaries be determined by the same set of streamlines. Okay, this means that the number of fluid particles crossing these surfaces as indicated at PRQ is same. Okay, the number of fluid particles which cross these planes are same. If the area of cross section at these points, if it is represented by AP, AR and AQ. Okay, and speeds of fluid particles, it is given by VP, VR and VQ. Then mass of the fluid delta MP crossing at AP in a small interval of time, delta T is given by, so the mass of the fluid, that is delta MP, which is crossing AP in a small interval of time, delta T, that is given by delta P AP and the velocity Vp into delta T. Okay. Similarly, the mass of fluid delta mr flowing or crossing at AR in a small interval of time, delta T is given by, yes, that is given by delta mr is, okay, that is given by delta R, AR and V R into delta T, isn't it? And the mass of the fluid crossing the plane AQ is given by delta MQ, which is given by delta Q AQ VQ into delta T. So crossing at AQ. The mass of liquid flowing out equals the mass flowing in, isn't it? The liquid which is flowing out is equal to the liquid which is flowing in. So we can say as a delta P AP VP delta T is equal to delta R AR VR delta T is equal to delta Q AQ VQ delta T. So for the flow of incompressible fluids, we can write it as delta P is equal to delta R is equal to delta Q, isn't it? And this, if you put this in this above equation, we'll get a final equation that is equal to APVP is equal to ARVR, that is equal to AQVQ, which is called equation of continuity, and it is a statement of conservation of mass in flow of incompressible fluids. In general, we can say AV is equal to constant. Okay. This is the volume or flow rate we can say, and it remains constant throughout the pipe of flow. Narrower portions where the streamlines are closely spaced, the velocity will be higher, and it's vice versa. Okay. And from this figure B, one thing is clear that from this figure B, one thing is clear that AR is greater than AQ. So we can write VR is less than VQ. The fluid is accelerated while passing from R to Q. See, larger the area, velocity will be lesser compared to the area which is smaller. Here velocity will be more because AV must is equal to constant. In order to maintain that relation, that it will vary according to that. So this is associated with the change in pressure in fluid flow in horizontal pipes. Okay. Steady flow is achieved at low flow speeds beyond a limiting value called critical speed. This flow loses that steadiness and it becomes turbulent. We can see this kind of turbulent flow in when a fast flowing stream encounters rocks. Okay. Small foamy whirlpool like regions called as white water rapids are formed. Round forms it will form, right? So in this figure you can see streamlines for typical flows. It describes a laminar flow where velocities at different points in the fluid may have different magnitudes but the directions are parallel. And coming to the turbulent flow, you can see in this it is a jet of air striking a flat plate which is placed perpendicular to it. So this is a turbulent flow example. Okay. So now let us see what is Bernoulli's principle. See, fluid flow is not a simple phenomena, it's a complex phenomenon. It includes so many concepts in it. So, but we can obtain some useful properties for steady or streamlined flows using the conservation of energy. Okay, you just consider a fluid which is moving in a pipe. This is, you just consider this figure. So consider a fluid which is moving in a pipe of varying cross sectional area. Let the pipe be at varying heights, as you can see here. Here the pipe is at a height h1, and here the pipe is at a height h2. Okay, so we now suppose that an incompressible fluid is flowing through the pipe in a steady flow. So its velocity must change as a consequence of equation of continuity. A force is required to produce this acceleration, which is caused by the fluid surrounding it. The pressure must be different at different regions because they are at different heights. So Bernoulli's equation is a general expression that relates the pressure difference between 2 points in a pipe to both velocity changes as well as elevation changes, which means kinetic energy change as well as for height change. So it relates that change in the pressure at two different ends. Okay, so the Swiss physicist Daniel Bernoulli developed this relationship in 1738. Okay, so here they'll express the relationship between the, what we can say, the pressure at two different points, the pressure difference. So consider the flow at two regions, that is region 1, that is the flow at BC here, and the flow at D, okay, B to D, in an infinitely small time interval delta t. So this fluid would have moved. Suppose V1 is the speed at B and V2 is the speed at D. Then fluid initially at B has moved a distance of V1 into delta t to C. And similarly, in that same time interval, the fluid initially at D moves to E, a distance which is equal to V2 into delta T, isn't it? That is given in this figure. They have written here V1 into delta T, V2 into delta T. So pressures P1 and P2, they act on the plane faces of areas A1 and A2 binding the two regions. That is also shown here. The pressure P1 here and the pressure P2 here, isn't it? So the work done on the fluid at the left end, which means at BC, is given as W1. We consider the work done at BC is BW1, which is given by P1 A1 into V1 delta T. Okay, so we can write it as P1 into delta V. Since the same volume delta V passes through both the regions. And similarly, the work done by the fluid at the other end, that is D, is, we'll consider it as W2. So which is given by P2 A2 V2 into delta T. So this one we can write it as P2 into delta V, isn't it? So the work done on the fluid is minus P2 into delta V. So we can write the total work done on the fluid as W1 minus W2. That is P1 minus P2 into delta V. So part of this work goes into changing the kinetic energy of the fluid and part goes into changing gravitational potential energy. Okay, this energy is used for two different, one for changing the kinetic energy and the other one is used for changing the potential energy. So if the density of the fluid is rho, and we can write delta m as given by, we know the equation, that is rho a1 into v1 delta t, or in other words we can write it as rho into delta v, that is the volume, is the mass which is passing through the pipe in time delta t. The change in gravitational potential energy is, so we can write the change in gravitational potential energy as delta U, which is given by Pg, which is given by the change in gravitational potential energy rho g delta V into H2 minus H1. The change in kinetic energy, that is delta K 1 by 2 1 by 2 rho delta V V2 square minus V1 square. Isn't it? This is the change. We can employ the work energy theorem to this volume of fluid, and this yields the result, that is given by P1 minus P2 into delta V is equal to 1 by 2 rho delta V into V2 square minus V1 square plus rho G delta V H2 minus H1. This is by the work energy theorem. So we now divide each term by delta V. Okay, and then we'll get the simplified expression, that is P1 minus P2 is equal to 1 by 2 rho V2 square minus V1 square. Okay, we can rearrange the above terms to obtain the equation, that is P1 plus 1 by 2 rho V1 square rho G H1 is equal to P2 plus 1 by 2 rho V2 square, that is rho G H2. This is the Bernoulli's equation. Okay. 1 and 2 refers to any two locations along the pipeline. We may write the expression in general as P plus 1 by 2 rho V square plus rho GH is equal to constant. This is the general expression. Okay. In other words, the Bernoulli's relation may be stated as follows. As we move along a streamline, the sum of the pressure, the kinetic energy per unit volume, as well as the potential energy per unit volume remains constant. So note that in applying the energy conservation principle, there is an assumption that no energy is lost due to friction. But in fact, when fluids flow, some energy does get lost due to the internal friction. Okay, this arises due to the fact that in a fluid flow, the different layers of the fluid flow with different velocities, and these layers they exert frictional forces on each other, resulting in a loss of energy. This property of fluid we call it as viscosity. Again, we'll discuss about it in detail. Okay. The lost kinetic energy of the fluid gets converted into heat energy. Thus, Bernoulli's equation ideally applies to fluids with zero viscosity, or we can say non-viscous fluids. Another restriction on application of Bernoulli's theorem is that the fluids must be incompressible, as the elastic energy of the fluid is also not taken into consideration when we are applying this Bernoulli's theorem. In practice, it has a large number of useful applications and it can help to explain a wide variety of phenomena for low viscosity incompressible fluids. Okay, Bernoulli's equation also does not hold good for non-steady or even for turbulent flows, because in that situation velocity and pressure are constantly fluctuating with time. When fluid is at rest, its velocity is zero everywhere. At that time, Bernoulli's principle becomes when fluid is at rest.